A vast section of Earth's surface, hidden beneath thousands of meters of ocean water, is showing signs of strain that were not expected to appear within a human lifetime. Instruments designed to detect subtle shifts in gravity, temperature, and motion are now recording patterns that do not align with long-standing assumptions about how the largest tectonic plate on the planet behaves. The Pacific Plate, spanning roughly 180 million square kilometers, or about 69 million square miles, has long been treated as a stable foundation beneath the ocean basin, but recent measurements indicate that something far more dynamic is unfolding deep below the surface. How can a structure that supports nearly one-third of the planet begin to bend from within? What mechanisms could generate fractures thousands of meters below sea level without immediate surface disruption? And if the central ocean floor is no longer stable, what does that mean for the systems above it that depend on that stability? For decades, geological models described tectonic plates as largely rigid slabs, moving slowly across the Earth's mantle at rates measured in centimeters per year. The Pacific Plate, moving at approximately 10 centimeters annually, or about 4 inches per year, has been among the fastest. Its interactions along the edges where it collides with continental plates or sinks beneath them have been well documented. These boundaries form the Pacific Ring of Fire, a zone responsible for nearly 90% of the world's active volcanoes and a significant share of seismic activity. Yet the central region of this plate, far from those boundaries, was assumed to be relatively inactive. That assumption is now being challenged by data gathered from satellites, deep-sea sensors, and autonomous exploration systems, operating at depth reaching 6,000 meters or nearly 20,000 feet. Satellite altimetry, which measures slight changes in ocean surface height, has revealed subtle but persistent vertical oscillations across remote sections of the Pacific. These changes are measured in centimeters, but their scale extends across distances of up to 800 kilometers, or about 500 miles. The ocean surface itself is not rising due to waves or weather, but rather responding to movements in the solid crust below. Laser mapping of the seafloor confirms that sections of the oceanic crust are flexing. In certain areas, the basalt layer that forms the ocean floor appears to be thinning and bending downward under pressure. These deformations are not isolated. They form elongated zones stretching across vast distances, indicating that stress is being distributed across the plate's interior rather than confined to its edges. Deep beneath these regions, monitoring stations have detected continuous low-frequency vibrations originating from depths of around 10 kilometers, or approximately 6 miles within the crust. These signals differ from typical earthquake patterns. Instead of sudden, high-energy releases, they represent sustained mechanical movement, as if the rock itself is gradually shifting under pressure. At the same time, temperature sensors placed in deep ocean water have recorded unexpected increases. In areas where the seafloor is fracturing, heat appears to be escaping through newly formed cracks. These thermal anomalies are small in absolute terms, often just a few degrees Celsius, but they are significant given the normally stable conditions of the deep ocean, where temperatures typically hover just above freezing, around 2 degrees Celsius or 36 degrees Fahrenheit. The presence of heat suggests that the source of these changes lies deeper still, within the mantle. Beneath the Pacific Plate, mantle material reaches temperatures of approximately 1,200 degrees Celsius or about 2,190 degrees Fahrenheit. Under such conditions, solid rock behaves less like a brittle material and more like a viscous substance capable of slow flow. This movement exerts upward pressure on the overlying crust. As this heat rises, it weakens the lithosphere, the rigid outer shell of the Earth. In regions where the crust is already thin, this weakening can lead to deformation. The basalt that forms the ocean floor begins to lose its structural integrity, allowing it to bend and stretch. Over time, this process can produce fractures that extend for hundreds of kilometers. Data from the Manihiki Plateau and the Clipperton Fracture Zone show stress patterns that diverge from established geophysical models. Pressure sensors in these regions record continuous micropulsations, indicating that the crust is under constant strain. Rather than experiencing occasional stress followed by release, these areas appear to be in a state of ongoing deformation. Autonomous underwater vehicles have provided direct visual confirmation of these changes. Operating at depths approaching 6,000 meters, these machines have documented fresh fractures in the basaltic crust. The exposed rock surfaces lack sediment cover, indicating that the breaks occurred recently, within timeframes measured in years rather than millennia. When seawater enters these fractures, it encounters rock that remains heated from below. This interaction produces rapid thermal exchange, generating localized pressure changes within the cracks. The result is a series of hydraulic shocks that can further weaken the surrounding material, promoting additional fracturing. Alongside these structural changes, gas emissions have been detected rising from the seafloor. Methane and carbon dioxide, trapped beneath the crust, are being released through these fractures. Measurements indicate that these emissions are increasing in frequency and distribution, suggesting that internal pressure is being vented through newly formed pathways. The scale of these processes points to a broader transformation. Instead of a single, uniform plate, the Pacific structure may be developing internal segmentation. Zones of weakness are forming, effectively dividing the plate into smaller sections that can move independently under stress. This fragmentation does not occur suddenly but progresses through incremental changes that accumulate over time. The forces driving this transformation are not limited to internal heat. External pressures also play a role. The Pacific plate is bounded by major continental masses, including Asia, Australia, and the Americas. These surrounding plates exert compressional forces, effectively squeezing the Pacific plate from multiple directions. This compression adds to the stress generated by rising mantle material, creating a complex system of forces acting simultaneously on the crust. As a result, regions that were once considered stable are now exhibiting measurable movement. Digital elevation models show that some sections of the seafloor are rising slightly, while others are subsiding. These vertical shifts, though small in magnitude, have implications for ocean circulation. The ocean floor is not a flat surface. Its contours guide the movement of deep water currents, which play a critical role in distributing heat across the planet. Changes in seafloor topography can alter these current pathways, potentially affecting global climate patterns. In certain areas, warming of deep ocean water has already been observed. This warming is linked to geothermal heat escaping through fractures. As warmer water rises, it can disrupt established circulation patterns, influencing temperature distribution across large regions. These changes are not confined to the deep ocean. Surface conditions may also be affected over time. Variations in ocean temperature can influence atmospheric behavior, contributing to shifts in weather patterns. Regions that depend on stable ocean-driven climate systems may experience increased variability, including altered rainfall patterns and changes in storm intensity. Coastal regions face additional challenges. The stability of shorelines depends in part on the structure of the seafloor just offshore. If that structure changes, it can influence how waves and tides interact with the coast. In some cases, this can amplify the impact of storm surges, increasing the risk of flooding. Maritime infrastructure is also exposed to these risks. Ports, shipping lanes, and underwater communication systems rely on predictable ocean conditions. As the seafloor shifts, these systems may need to adapt to new realities. Insurance data already reflects growing uncertainty, with increased costs associated with ocean-based operations. One of the most significant aspects of these developments is the rate at which they are occurring. Geological processes are typically measured over millions of years. However, current observations suggest that some changes in the Pacific are unfolding on timescales that can be tracked within decades. Satellite measurements indicate that deformation zones are expanding more rapidly than earlier models predicted. Areas that showed no signs of activity in previous decades are now displaying continuous movement. This acceleration raises questions about how the system will evolve in the coming years. Gravitational data provides further evidence of change. Subtle variations in Earth's gravitational field have been detected over parts of the Pacific. These variations correspond to shifts in mass distribution within the crust, supporting the idea that material is being redistributed as the plate deforms. Historical geological records offer context for these observations. Sediment cores extracted from the ocean floor contain evidence of past episodes of rapid deformation. These events appear to have occurred in pulses, during which stress built up over long periods was released relatively quickly. Isotopic analysis of volcanic rocks from regions such as Polynesia indicates that material from deep within the mantle has reached the surface in the past. These findings suggest that the processes currently being observed are not entirely new, but part of a recurring pattern in Earth's geological history. What distinguishes the present situation is the ability to observe these processes in real time. Advances in satellite technology, deep-sea exploration, and data analysis have made it possible to detect changes that would have gone unnoticed in earlier decades. At depths where sunlight does not penetrate and pressures exceed 600 atmospheres, the ocean floor is undergoing transformations that challenge established models of planetary behavior. The Pacific Plate, once regarded as a stable platform, is revealing a level of internal complexity that is only now coming into focus. Energy continues to accumulate within the crust as it bends and stretches. Fractures deepen and new ones form, creating an interconnected network of weaknesses. The interaction between heat, pressure, and structural stress is producing conditions that could lead to further changes in the geometry of the ocean floor. As monitoring systems continue to collect data, patterns are emerging that point to a coordinated process rather than isolated anomalies. Temperature increases, gas emissions, seismic activity, and physical deformation all appear to be linked components of a larger system. The implications extend beyond geology. The ocean is a central element of Earth's climate system, and any changes to its structure can have cascading effects. From the movement of currents to the stability of coastlines, the influence of these deep-sea processes reaches far beyond their point of origin. In regions where the crust is thinning, the mechanical strength of the plate is approaching its limits. The combination of internal heat and external pressure is creating conditions under which the rock can no longer maintain its original form. As this threshold is approached, the likelihood of more pronounced structural changes increases. Measurements from multiple sources now indicate that the Pacific Plate is not behaving as a single rigid entity. Instead, it is responding to a complex set of forces that are reshaping it from within. The emergence of rift-like features in the central ocean basin suggests that the process of fragmentation may already be underway, though at a scale that remains largely invisible from the surface. As the pattern of deformation continues to expand across the Pacific basin, the structural implications are becoming increasingly difficult to reconcile with older models that treated the plate as a single coherent unit. Measurements collected over the past several years indicate that the zones of weakness are not only widening but also deepening, with some fractures extending several kilometers into the crust, in some cases approaching depths of 10 kilometers, or roughly 6 miles. These are not superficial cracks limited to the uppermost layers. They penetrate into regions where temperature and pressure conditions fundamentally alter how rock behaves. In these environments, basalt does not fracture in the brittle manner observed near the surface. Instead, it undergoes a transition into a more ductile state, where deformation can occur gradually before failure. This creates a scenario in which stress accumulates over wide areas rather than being confined to a single fault line. When release does occur, it may not follow the familiar pattern of a localized earthquake. Instead, it could involve distributed movement across a broad section of the seafloor, shifting entire regions of crust by measurable distances. The energy stored within these deformed regions is considerable. Calculations based on stress accumulation and crustal thickness suggest that the total mechanical energy involved rivals that of the largest recorded seismic events, but spread across a much larger area. This distribution reduces the likelihood of a single, catastrophic rupture, while increasing the probability of sustained, multi-phase adjustments in the plate's structure. In practical terms, this means the ocean floor may continue to shift in a series of incremental but persistent movements rather than one isolated event. Evidence for this type of behavior is already visible in long-term seismic records. Instead of isolated spikes, monitoring stations are detecting extended periods of low-frequency activity lasting days or even weeks. These signals indicate that the rocks are undergoing continuous adjustment, a process sometimes referred to as slow slip, though on a scale that exceeds previously documented examples. The cumulative effect of these movements can alter the geometry of the seafloor in ways that were not anticipated within conventional frameworks. One of the more significant consequences of this restructuring lies in its potential to create new regions of divergence within the plate. As the crust stretches and thins, it may reach a point where it can no longer maintain continuity. At that stage, magma from the mantle can begin to rise through the weakness, solidifying to form new oceanic crust. This process is typically associated with mid-ocean ridges, yet current observations suggest that similar activity may be initiating within the interior of the Pacific Plate itself. If such divergent zones continue to develop, they could eventually form linear features comparable to established spreading centers. These would not appear instantly as prominent ridges, but would evolve gradually, beginning as narrow bands of deformation that widen over time. The presence of elevated heat flow combined with gas emissions and fracturing indicates that the conditions necessary for this transition are already present in several locations. The formation of new crust within the Central Pacific would represent a fundamental shift in how the plate operates. Instead of acting solely as a passive conveyor of material towards subduction zones, it would also become a site of active generation. This dual role complicates predictions about future movement, as it introduces additional variables into an already complex system. Changes at the level of the seafloor inevitably influence the behavior of the overlying ocean. One of the most immediate effects is the alteration of deep water pathways. Ocean currents that travel thousands of kilometers or more than 6,000 miles rely on the contours of the seafloor to guide their movement. Even slight modifications in depth or gradient can redirect these flows, leading to shifts in how heat and nutrients are distributed. Recent observations have already identified anomalies in deep current speed and direction within affected regions. In some cases, currents that were previously stable have slowed or diverted, creating pockets of water with different temperature and chemical characteristics. These changes can propagate upward through the water column, eventually influencing surface conditions. The ocean plays a central role in regulating the planet's climate by absorbing, storing, and redistributing heat. When this system is disrupted, the effects can extend far beyond the immediate vicinity of the changes. Warmer deep water rising toward the surface can enhance evaporation rates, contributing to increased atmospheric moisture. In turn, this can influence precipitation patterns, leading to shifts in rainfall distribution across continents. Regions that depend on predictable seasonal cycles may experience increased variability. Extended dry periods could be followed by intense rainfall events, placing stress on agricultural systems and water management infrastructure. Coastal areas, already sensitive to sea level changes, may face additional challenges as altered currents affect local sea surface and wave dynamics. Another factor to consider is the interaction between seafloor deformation and tidal forces. The shape of the ocean basin influences how tidal energy is distributed. As the seafloor changes, it can modify resonance patterns, potentially amplifying tidal ranges in certain locations. While these changes are expected to be gradual, their cumulative effect over time could increase the frequency of coastal flooding during high tide conditions. Maritime operations are also affected by these developments. Subsea cables, which carry the majority of global data traffic, are laid across the ocean floor with the assumption of relative stability. Regions of active deformation introduce new risks, as shifting rocks can place stress on these lines, increasing the likelihood of damage. Repair operations at depths exceeding several thousand meters are complex and costly, adding to the vulnerability of global communication networks. Shipping routes, though primarily influenced by surface conditions, may also need to adapt. Changes in current patterns can affect travel times and fuel consumption, while variations in sea state can influence navigational safety. Insurance assessments for maritime activities are beginning to incorporate geological factors that were previously considered negligible. In parallel with these practical concerns, there is a growing recognition that the processes underway may represent a stage in a larger cycle of planetary evolution. Geological records indicate that Earth's surface has undergone repeated episodes of fragmentation and reconfiguration over hundreds of millions of years. Continents have formed, broken apart, and reassembled in different configurations driven by the movement of tectonic plates. The Pacific Plate itself is relatively young in geological terms, with much of its crust formed within the past 200 million years. Its current size and structure are the result of continuous processes of creation and destruction at its boundaries. The emergence of internal deformation suggests that it may be entering a new phase, one in which its internal dynamics play a more prominent role. If you found this breakdown informative and want more deep, fact-driven coverage like this, make sure to like, share, and subscribe, and tap that hype icon to help this video reach a wider audience.